Welcome back to ECE 501B. Homework number 7. If you aren't paying attention with D2L all the time, maybe you didn't see that that has been posted. I hope it's there. I thought I posted it this weekend, but it's not due Wednesday. I'll give you a weekend to work on that. It's due a week from today, and that will be on the 4th. We will try to have a review session. Stay tuned as to where it's located for exam number 2, but that will be, the review session will be a week from today. The review, or the exam number 2 is a week from Wednesday. And the material will really be material from homeworks 5, 6, and 7, which is roughly chapters 5 and 6. Eigenvalues, eigenvectors, and then inner product spaces and what we can do on those inner product spaces, or some of the things that we can do with that. And I would like to get finished with material. I don't think we will do anything in chapter 7 on the exam, but I would like to get to chapter 7 sometime today is the plan. Let's recap to start today with the definitions or the theorems associated and the statements associated with linear functionals, which is you can create that by means of an inner product, and the adjoint. Then we will show that the adjoint map is indeed linear, which is a good thing. And then we'll simply write down a result that relates the range space and null space of these different of these maps, these different linear maps, the map T and its adjoint. Then we will simply present the fact that the matrix representation of a linear map, if we call that A, and if we want the adjoint, or the matrix representation of that adjoint, which is also a linear map, that will actually be the complex conjugate transpose of the matrix A. And maybe we'll work some examples or look at some examples illustrating that, just so that you start to see a concrete representation of maybe these abstract quantities or concepts. As far as a linear map, you should be comfortable with a linear map, but now what is this object called an adjoint? And we'll work through some examples with that is the plan before we move into chapter 7, which is we sort of learn where the space that we're dealing with, and then we move into maps between spaces. We've just now, once we get to this point, we will have completed chapter 6, which is a new space, an inner product space. It's basically a vector space with an inner product. Once we have that playing field available to us, now let's start talking about operators on that inner product space, and that's chapter 7. The first topic being self-adjoint operators, which really just means that the linear map is equal to the adjoint of that map. That's what it means to be a self-adjoint operator. As a review, just to get us sort of back up to speed and thinking linear algebra, Theorem 645 deals with linear functionals. If we're given a linear functional, which is really just a map from our vector space V into the field of numbers that that vector space is on, so we're really just mapping from a vector space to a scalar, then given some linear functional phi, and that may not be in the form of a sort of this inner product of a row and a column vector. It may not be in that, let's say, conventional vector space. Maybe it's some abstract vector space. We can actually find, though, a basically row vector W such that the inner product of U with W is the same as what you would do if you created this linear or you had this linear functional phi and you process that with this vector u. The w is a unique vector, and it's really just the linear functional applied to a orthonormal basis of our vector space V. That gives us these scalars that we then complex conjugate, and those now scale these orthonormal basis vectors, and that's our unique vector W. And if somebody wants to then find a vector W, which now we can just form the inner product with, then we can build that vector W using this technique. So it really means we need to find an orthonormal basis for our vector space, capital V. And once we have that, then if somebody gives us a linear functional phi, we can find a vector W defined by that representation to allow us to simply form inner products to create the same value, scalar value. That's the linear functional idea. We then played with or introduced this notion of an adjoint operator, a map. We haven't yet shown that it's a linear map, but I'm using that just to get us started. If we're given a linear map T from V to W, and now we have two inner product spaces, V and W. Those are now both vector spaces enhanced with an inner product. The adjoint of this linear map T is what we're calling T dagger, and now that maps us from W into V. And it does this relationship by equating scalars. If we take a V and we take a W, I feel like a cheerleader now. Give me a V, give me a W. That's not what that spells, but now we can create an inner product, right? So we can say TV, inner product with W, is going to give us a scalar. Well, the adjoint, when operated on W, and inner product with V gives us the same scalar. That's the definition of the adjoint. Now, before we look at some examples, let's present basically the rest of chapter 6. And the first thing that we want to talk about is showing or verifying that indeed this adjoint map is a linear map. And that's supposed to be a dagger. So is T dagger, is the adjoint a linear map? Let's look at just basically the governing relationships. We need, or what do we need to show if a map is a linear map? What properties does it need to possess? Additivity and homogeneity. So let's look at those two in turn. In terms of additivity, suppose we have TV inner product with W1 and W2. Well, because of additivity in the second slot, that's equal to TV W1 plus the inner product, of TV with W2. And now this looks like something that we can apply the adjoint definition to. We're used to having just two vectors inside, or a first slot and a second slot quantity in the inner product. Now, by definition of the adjoint, what's this first one going to be equal to? If I give you a V, now what do you give me? If we're in the stadium and I'm listening for your callback, If I give you a V and this is the definition of the adjoint, what's this first inner product supposed to equal? Adjoint W1. Is that okay? That's just the definition of the adjoint. If we do the same thing, this is now V T, or the adjoint of T W2. But now we can play with the additivity in the second slot again. And that's now V of T dagger W1 plus T dagger W2. But what's the left? If we looked at this quantity right here, what would that have to equal in terms of an adjoint expression? So if we looked at the left-hand side, which I've now highlighted in yellow, in terms of the adjoint, what is that equal to? It's now T dagger applied to W1 plus W2 by the definition of the adjoint. And now if we simply compare the second slot in those two derivations, we can see that, oh, this is now really a linear operator. This is saying T dagger applied to W1 plus W2 is T dagger W1 plus T dagger W2. So now we know that T dagger W1 plus W2 is equal to T dagger W1 plus T dagger W2, and that's our check on additivity. And let's do the same kind of process to show homogeneity. If I now take this TV and I scale a vector W by the scalar A, now if I pull out a scalar from the second slot, what does that give me? That's the conjugate homogeneity of the second slot, right? So that A needs to be conjugated, and then it will be TVW. But what now, if I just keep that A star out front for now, what's the TVW look like if I apply the definition of the adjoint? That's just V T dagger W. But now what if I apply the conjugate homogeneity to the second slot? If I slide that scalar back in now I need to conjugate it to go back in, and the conjugate of A star is just A itself. So this is now equal to V A T dagger W. Again, what's the left-hand side that we started with? If we use the definition of the adjoint, that's now V T dagger of AW. And now if we simply compare like we've done before, the second slot vectors, now we have our homogeneity property demonstrated. For T dagger of AW is actually equal to A T dagger W. And now my earlier recall or recap discussion is valid. I've now shown that if I said I have a T dagger that's mapping between W and V, that belongs to this set of linear maps from W to V. And that's what I'm saying. So in general, if I have a linear map T, and V and W are not necessarily the same size, are they? Or they're not necessarily the same. These are maps, not yet operators. Then now we've just shown that if we have the adjoint, that's now a linear map between W and V. And that's nice to know. Now if we have an adjoint operator, we know that we can apply all these linearity properties to it. It's a linear operator or a linear map. A linear map, and then a more specific, it's a linear operator. Because an operator maps from a space back into itself. And that's a more restrictive class of operators than just of maps than a linear map. But it is a linear map. Now the adjoint has several properties that I'm really just going to list, but it's nice to be able to have these so that you can simply apply those. So the adjoint has the following properties. One that we've can show, but we won't, we'll just state it, and that's additivity. If we now had S and T as linear maps and we added those, but then we took the adjoint of their sum, that's now the sum of the two adjoints, S and T. And that's true for all S and T. Now, what do you know has to be true? These have to be maps between the same inner product spaces, V and W. So S and T both have to belong to this set of linear maps, V and W. You can't be dealing with maps between different vector space or inner product spaces and adding them. It just doesn't make sense. They have to be compatible if we were talking matrices. Second property is the conjugate homogeneity property. And that says then if I take a scaled version of our linear map T and take the adjoint of that, then I get the scalar conjugated, or its complex conjugate, scaling the original map's adjoint. And that's for all A in our field of numbers and T in our collection of maps. If you really get into adjoints, maybe you want to adjoint an adjoint. And so what do you think that's going to give you? If I now have the adjoint of a linear map, but now I take the adjoint of that, that's going to give us our original map back. That's sort of nice to know. Another one is, and we'll use these properties when we're deriving some other results, the identity If I had the identity map and I took the adjoint of that, what's that going to produce? It better just give me the identity map back. The identity map just takes me from a vector back to that same vector, and now if I take the adjoint of that, I better get the same map. Finally, with some of these properties, what happens if we have the product of two maps and we take the adjoint of that? Suppose we form the product of linear maps S and T and we take the adjoint of those. Now that's sort of similar to how you deal with inverses in terms of matrices. What happens to the sort of order of those operations? They basically switch places, don't they? So now we have T adjoint times the adjoint of S, and that's for all. And now these could be different in terms of where they belong. Let's say that T is now an operator from V to W, and S, what's it? So if we simply look at the first operator before we take the adjoint, we first process a vector with T, and then we process it with S. So the result of an operator operating on a vector that we now know is V, we end up in W. So S better take something in W and take it somewhere else. Let's call it U. So this will now be from W to U. Those are some properties. Now let's look at some characteristics of these two sets of linear maps. Maybe you will find these more useful than interesting, so let me say there is an interesting, or maybe you'll say useful. Maybe you don't find this interesting, but you should if you're in this class, right? So now what are some of these relationships between these different maps and their ranges and null spaces, etc.? And I'll just say sort of this null slash range, and those are spaces of T and its adjoint. And this is collected, these relationships are stated in this proposition 646. First, let's just start with a linear map between V and W. Then we have four different relationships. One is if we looked at the null space of T dagger, that's going to actually be the same as looking at the range space of our original map, its orthogonal complement. You give me a linear map, T, and I can find its range space. Then you look at the orthogonal complement to that, which if you know V is n-dimensional and maybe its range is M, then you know how big that orthogonal complement is. Well, now vectors in that orthogonal complement are equivalent to the vectors in the null space of the adjoint of T. And we just have a lot of different relationships like that. number 2 is that the range of the adjoint operator is actually the orthogonal complement of the null space of the original operator T. If we wanted to look at the null space of T, the vectors in that, that's the same as the range of the adjoint's orthogonal complement. And finally, if we look at the range of T, then that's going to be the same as the null space of the adjoint's orthogonal complement, or the orthogonal complement of the null space of the adjoint. It's a mouthful. Let's prove a few of these, and we can actually, if you look at some of these, for example, what if we, well, which one do I want to take? If I took the orthogonal complement of the first one, then that's going to give me the range of T on the right, and on the left, it's going to give me the orthogonal complement of the null space of T. So if I prove a couple of these, then we can get the others by just taking the orthogonal complement of the ones I've proven. That's sort of the idea. How about we look at the first one, which is now off the screen, but that was the null space of the adjoint. We want to show that that's equivalent to or equal to the vectors that are in the orthogonal complement of the range of T. And we sort of know what all of those mean. First, let's select a vector in the null space of the adjoint operator. Let's just say that we pick a W that belongs to the null space of the adjoint. If that's the case, then we know that if we looked at T dagger W, what's that going to give me? We picked W to be in the null space of this operator, which is the adjoint of T, so that better, by the definition of how we selected W, that's going to be 0. Well, really now what I'm going to do is I'm going to say, let's look at V, inner product with the 0 element. Because we know what the 0 element, we can rewrite the 0 element as T dagger W. That's really what I'm doing in this next step. So now I can basically say that V inner product with T dagger W, what do you know that equals? This is equal to 0, isn't it? So this better be equal to 0, and that's for all V in our original vector space, capital V. But now what's the definition of the adjoint applied to that last equation? If I now play this tape in reverse, we've been going TV inner product with W is equal to the inner product of V with T dagger W. So if this is 0, then we know that TVW is equal to 0 by the definition of the adjoint. And that's for all vectors V. But what's that tell us? That now tells us that W and whatever this first slot is as a vector, those are orthogonal, aren't they? But what comes out of TV? The only way that, or the only place you get when you go from operating on V with T is the range of T. So now we're saying that W is in the, or is it orthogonal to the range of T. So now we're saying that W is an element of the orthogonal complement of the range of T. W is orthogonal to TV, and TV is spanning the range of T. And that's really what we wanted to show, because we started with W being in the null space of the adjoint of T. So the null of the adjoint of T is the same or is equal to the orthogonal complement of the range space of T. Is that okay? And now we can basically do 3 the same way. If we looked at 3, that's also dealing with the null space, and we'll see where that takes us. So if we now look at verifying or proving step 3, now we can pick a V in the null space of T, just like we did before. And if that's the case, now we know TV is equal to 0 by definition of the choice of V. And doing what we've done before, knowing that 0 inner product with W is equal to 0, now that says that if we have TV inner product with W, that's equal to 0, and that's true for all W in W. And what's going to be our next step? Now we just apply the definition of the adjoint to this inner product. So TV inner product with W is equal to, by definition of the inner product, or I'm sorry, definition of the adjoint, we now know that V is orthogonal to T dagger applied to W. But what is T dagger of W? That's everything in the range of T dagger, or the adjoint of T. So now we know that V is orthogonal to that space. So V, it belongs to the orthogonal complement of T, the range, the orthogonal complement of the range of T dagger. That's V. Or now that's really wherever we picked V. V we picked to be in the null space of T, and now we're concluding that V is also in the orthogonal complement of the range of the adjoint of T. And that's what we wanted to show. The null space of T is the same as the orthogonal complement of the range space. Well, we're not quite done, but if we simply, that's the end of 3, and now if we take the orthogonal complement of 1 and 3, we're back to 2 and 4, and so we'll not do any more of that. Meaning that maybe I was premature on this little block here, but taking orthogonal complements, So if we take the orthogonal complements of both sides of the remaining entries, that basically completes the proof, because that'll give us back what we've just now shown. What we've been playing with a lot are just these generic linear maps, T and its adjoint. Let's now think about what that looks like in terms of a matrix representation. So now that's going to give us another proposition. First, though, let me say there's a useful relationship between the matrix representation of a map and the matrix representation of that map's adjoint. And that's proposition 647. In proposition 647, let's now consider two sets of bases. Let's say that A, and let's even be more specific, let's let A be an orthonormal basis on V, and let's let B be an orthonormal basis on W. Once we have those orthonormal basis sets, so A is a set of vectors, B is a set of vectors, then if we wanted to look at the matrix representation of the adjoint operator of T from the base, using the basis vectors in W to the basis vectors in V, then that matrix representation is actually the conjugate transpose, or the transpose conjugate. Doesn't matter which way you do it, you'll get the same result. So is the conjugate transpose of the matrix representation of T going from two different basis vectors A and B. I'll refer you to the text for the proof. What I want to do is sort of play with or introduce some examples. But before we do that, we can just sort of state this, what do we mean by the conjugate transpose of a matrix? Suppose I now said, okay, the conjugate transpose of a matrix, let's say it now looks like A, B, C, D, E, F. What's its conjugate transpose? Well, if you wanted to sort of cheat, you would say this, wouldn't you? You could say, okay, that's the conjugate transpose, but if we transpose that, then the rows become columns. But now we said we need to take the complex conjugate of each of those so that we now have A star, D star, B star, E star, C star, and F star. And what we've done is we've simply transposed this matrix representation of T and then take its complex conjugate. Or you could do it the other way. You could take the complex conjugates and then transpose. Let's look at some examples of this so that when we get into chapter 7, which basically we're ready to go into chapter 7, but when we get into that, when we start talking about self-adjoint, maybe it'll make a little bit more sense when we have something concrete to be thinking about. Let's look at, I'm going to call this adjoint example 1. Suppose that we now have a linear map T between a three-dimensional complex vector space and another three-dimensional complex vector space. And suppose this linear operator, T of x, y, z, is actually the following. When we take an x and a y and a z vector, that maps to 2x plus 1 minus I y in the first entry of the vector. Let's say the second entry, or the second coordinate, is now 3 plus 2ix minus 4iz. I'm running out of space, but hopefully you can see what I'm doing. And then the third coordinate will be 2ix plus 4 minus 3iy minus 3z. And what we want to do is find the adjoint of T. And what did we do last time? We put this into, we picked a vector, W, and in this case it would be in C3. We formed the inner product, and then we extracted out what needed to happen if we found V, inner product with the adjoint times W. Well, let's just see if we can find this based on what we said that the adjoint has to be. If we were looking at the matrix representation of T, what would that look like? Because if we had the matrix representation of T, then the adjoint would be easy. We would just transpose and conjugate that matrix. What is, so now here is our solution. What's the matrix? Well, I don't guess I want to go too far down. I want to keep the display. Let's say we call that A. What does that look like? We want to have a matrix A, which when operated on a vector, and now I like to think of this vector as a column vector, x, y, z. When x, y, z is operated on by A, the first coordinate of the output of that linear map becomes 2x plus 1 minus iy. Hopefully it's clear that A has to be 3 by 3. We're taking a 3 vector, x, y, z, into another vector, let's say x1, y1, z1, but x1 is now this 2x plus 1 minus iy, and what needs to be in this 3 by 3 matrix to make that happen in the first coordinate of the result? And now I'm really concentrating on the first row of this A matrix. I'm saying, what do we have in the first row, and I've already told you there's 3 columns in this matrix A. I have 3 entries, which when scaling x, y, z better give me 2x plus 1 minus I, y. What scales x? 2. So that's going to go right there. That's what's going to pull off the x sitting here to get me 2x. Now I want to add to that something times y. And that's just 1 minus I, isn't it? And what do I need to scale z with in the first coordinate of the output? I don't want any z, so I put a 0 there. Is it clear where that's coming from? How I obtained that first row of A, the matrix representation of that linear map, T. What's the second row? It has to produce that second coordinate when this matrix A is applied to x, y, z. I do get an x piece scaled. I do get a z piece scaled. I don't get a y piece, do I? What's my z piece? And my x piece? Is it clear where these are coming from? This is now my second row of this matrix representation of the linear map T. This is a linear map T, and now I want to be able to apply this matrix representation to any vector, in this case x, y, z, and produce this result. What's in the bottom row of the A matrix? What's in the first column of the bottom row? 2i. Is there anything non-zero in the second column? Four minus 3i. And what's in the third column of the third row? Is that clear what A is? Now we know how to get the matrix representation of the adjoint. The matrix representation of the adjoint of T is the complex conjugate transpose of this matrix we just created. So this A star transpose is going to be 3 by 3. And we know that the first column of that becomes the first row with those entries complex conjugated, or the complex conjugate of those entries. 2 becomes 2, doesn't it? Our diagonal, what happens to the diagonal when I transpose? It remains on the diagonal, and I just have to take the complex conjugate, and my diagonals were real, so that's the easy part. Now I have 2 points out of 100 on exam number 2, right? What's the 2-1 entry of A star transpose? I just take the 1-2 entry, conjugate it, and drop it down into the 1-2 or the 2-1 entry. Well, I kind of jumped around. I said I was working on the first column, didn't I? Of A. So now let's work on the first row of A star transpose. That means that this guy, the 1-2 entry, better be 3 minus 2i. What about the 1-3 entry? That also has a minus 2i and no real part. Is everybody okay with where these are coming from? What about the 2-3 entry? That's the conjugate of the 3-2 entry, which is 4 plus 3i. Is that okay? And now if somebody said, oh, well, what's the linear map of the adjoint? Now do you know how to create that or build that? What's the first coordinate? Now you just pull off these entries in the appropriate manner, meaning now we have 2x plus 3 minus 2iy minus 2iz, and that's the first entry or the first coordinate in that linear map, which is representing the adjoint of t. So that now we have 2x plus 3 minus 2iy minus 2iz. What's the second coordinate going to look like? And I'm going to actually go down because I know I'm going to run out of room. Well, maybe not. 1 plus ix plus 4 plus 3iz. And finally, the third coordinate in this linear map is going to be 4iy minus 3z. And that's now, if somebody gave you this, said, here's my linear map, give me the adjoint, it might not be completely obvious that you would write that down. But now, with this process, it was somewhat straightforward. It's just turn the crank. Is that okay? But now you have a picture or an image of a matrix representation of a linear map. This is now with the field of complex numbers. That's okay. And we have its adjoint. And if you wanted to write it as these linear maps, this is what it would look like. What if we wanted to get a better feel for this? All these complex numbers are complex. Let's do another example. Yes, question. So in a matrix, if we have the matrix representation of a linear map, if I now said what's the adjoint of that, then we just take the complex conjugate of the matrix representation that we started with. That's correct. So the adjoint operator is in matrix representation just the complex conjugate transpose of the matrix representation of the original map. Is that clear? It's a mouthful, but it's kind of fun. Now you can go home and start talking about adjoints and complex conjugate transpose, and everybody's going to go, would you just be quiet? No, I want to show you what I've learned. So let's do example 2. And this is going to be now adjoint example 2. And this one, since I want to maybe get even more warm and fuzzy with feeling about this, what if I say, now let's work with real vector spaces, R3 to R3. And why don't we just take what we already did? Let's say we have a map, T of x, y, z, and suppose I just take the real part of that previous example. Meaning, now my first coordinate of this linear map is going to be 2x plus y. The second coordinate is just going to be 3x, and the fourth coordinate is 4y minus 3z. I hope now it's pretty easy for you to quickly write down what the matrix representation of that linear map is. What's the first row going to look like? Or what are the dimensions of A? You better just be able to say what that is by looking at this T belonging to this set of linear maps from R3 to R3. So it's got to be square, and it's 3 by 3. What's A look like? What's the matrix representation of this map T? What's the first row? 2, 1, 0. What about the middle row? 3, 0, 0. And the third row? Now, if you want the adjoint, what would that look like? Well, that's just the complex conjugate. That's easy, isn't it? I can do that on this real matrix. And now I simply have to transpose it. So that now I have 2, 1, 0, 3, 0. That's a pretty ugly 3. What's in the second row? And what about my third row? So that now I can sort of pretty easily, I hope, write down what this adjoint looks like for this linear map. What's the first coordinate? Second coordinate? And the last coordinate. Is everybody comfortable with that? Now let's see what these maps actually do in terms of if you're thinking about, okay, I'm taking a 3 vector and I'm going to another 3 vector. So if we were in this room and we said the floor is our XY plane, and I don't know where we want to draw the coordinate, but if we have a right-hand rule, what do we want? How about because I think I know what I'm going to do, why don't we have the x-axis splitting the front and back of the classroom. Here's the positive x-axis, and now here's the y-axis, splitting the class into 2 halves. And the z is up above. Is that okay? So I have x, y, and z is up. All right. So now, with that visual, and this is going to be hard to visualize, I guess, if you're listening to this, but maybe you can sort of imagine that I'm standing up in front, and if I'm looking out to the class on my left, and I'm centered, let's say, from left to right, from my left is the x-axis going from me out to the left. The y-axis is coming from the middle of the room towards me, and then the z-axis is up and down, and it's up from the floor. Let's now say that that's what we're doing with this linear map, T, and let's just pick some vectors. Suppose that I pick a first vector V, and let me say that that's 1, 1, 0. And where is that? I'm standing at it, right? I'm 1 and 1. So that's basically where I lecture from, is 1, 1. All right, and let's let W whoops, that's not what I want. This isn't even consistent with my notes, but you don't know that, do you? Let's do this one. 0, 1, 1. Where's that? I have to play along, right? So now I'm on the y-axis, and I'm up in z. So in x coordinates, I'm 0. Is that okay? So I'm y1 and z1. So now I'm here with V and here for W. And now I want to form some operations with these maps. So if I looked at T, V, inner product with W, where's that going to put me in this? Well, what do we know? That's going to give me a scalar, isn't it? That's just going to give me a number. And it's going to be a real number because I'm playing with the real field. But where does TV take me? T was 2, 1, 0, 3, 0, 0, 0, 4, minus 3. And V was the XY plane, sort of. I was living just on the floor with that one. Right? I'm not vertical. So I'm vertically challenged with where I'm starting with V. It's on the floor. I guess I should have just said that's this spot on the floor. Where does that map to? So now I'm just combining the first two columns, aren't I? I'm just adding the first two columns in T is what this is saying. So if I add the two first coordinates or the first two columns, I get 2 plus 1. If I add the second coordinate in the first two, I get 3, and if I add the next one, I get a 4. Now I have to leave the room, don't I? If my dimensions were correct. But now I go over 3, up 3, and up 4. Well, that's this place over here, right? 3, 3, and 4. So I'm in three-dimensional space now, and I want to now take the inner product of that with W. That's 3, 3, 4, and what was W? That was the YZ plane, wasn't it? And let's just use the Euclidean inner product. So I have the first two coordinates multiplied together, added to the second two coordinates multiplied together, added to the third coordinates multiplied together. I have 0 plus 3 plus 4. 7. That's my scalar. So I started up here. I took the inner product of that with this, and I get 7. Now, the adjoint operated on W, which was here. I need to apply the adjoint map to this and inner product that with V, which was over here on the floor. That was just XY being 1, 1, 0. That better give me that same scalar. That's what I'm saying, in order for these ideas to be correct. All right, so let's do that. We're saying that we need to look at this inner product, right? That's the definition of our adjoint. And we found the adjoint T by taking the complex conjugate transpose, which if it's real, we don't need to worry about the conjugate part, the complex conjugate. So let's look at the adjoint that we produced operating on W, and W was the YZ plane. The adjoint was 2, 3, 0, 1, 0, 4, and 0, 0, minus 3. Bless you. I hope that was the right matrix. And this was now the YZ plane, meaning now I simply add the last two columns together, which says that I have 3, 4, and minus 3. That was pretty easy to add up, wasn't it? Because I had zeros matched up with some non-zero terms. Now I need to form the inner product of that with this point on the floor, which was V. So I guess if you're at home, you can play along, right? You can put a board game, you can be in your room, and you can start imagining what the X, Y, and the Z directions are. And speaking of board games, your next homework assignment has a board game on it. And you now need to figure out what properties you need to buy in order to win or to enhance your chances of winning. That's the idea on this homework problem. Where were we? Oh, we need to form an inner product. I really was trying to buy time to clean up that 4. This one now we do the same thing. It's the Euclidean inner product. We have 3 plus 4, 7, so we are what we said. So that seems to be working. What I want you to be thinking about, though, are these ideas about, and this is an example when we're in the field of real numbers, of a map, a matrix representation of that map, and its adjoint. So now we're ready to move into operators in chapter 3, operators on inner product spaces. And if we're talking about an operator, we now know we're taking from one vector space back into itself. That's chapter 7. Because now we've learned quite a bit about how to play with inner product spaces. That was the idea. Now we're ready to advance that by putting some operators onto these inner product spaces. Operators on inner product spaces. And maybe the room next door is playing a board game also. They seem to be having as much fun as we are. Okay, so now that we have this, let's look at the very first notion in chapter 7, which is a self-adjoint operator. Now, you thought we were throwing around some words before. Now you just wait. So now suppose we have an operator, T. Now we just have to worry about one inner product space, V, don't we? That operator, T, is self-adjoint. Or if you're reading other literature, it might be called Hermitian. I told you you'd be really excited about all the different words you're now going to be using. So now we have a Hermitian operator. That just means it's self-adjoint. An operator T is self-adjoint if T is equal to its adjoint. The operator is equal to its adjoint. And I hope that we can now, we're in a position to think about what this is really, how this is constraining these maps or linear operators T. This imposes certain constraints on the matrix representation of T. The matrix representation of T, and I don't need to, let's say, worry about the basis. It's the same, whatever. I mean, we're going from V to V. This matrix representation must be square. What are some reasons why that matrix representation needs to be square? Well, the first time we used operators, we said we were going from V to V, so we have to be going between similar vector spaces, which means our operator is square. So the matrix representation, or these operators, must be square, since this T is such that we go from V to V. Also, if I took the matrix representation of T, and let's just say that that was some n by m operator, then what do we know relative to the matrix representation of the adjoint? What's it belong to? What's F? That's m by n, and so that can't be equal, can it? Because these are just those are different shapes when m is not equal to n. So we know that these self-adjoint operators are square. When we talk about operators, we know they have to be square anyway. And we've already shown or stated that if the matrix representation of T was some A, B, C, now I have to remember my ABCs, huh? A, B, C, D, E, F, G, H, I. If that's the matrix representation of T, or yes, then what's the matrix representation of the adjoint? We transpose it, so I'll do the hard part. The diagonal stays put, doesn't it? But now I need to conjugate it. B comes over here, and C comes down in the third row. D goes up in the first row, as does G. F comes down in the third row, and H jumps up into the second row, doesn't it? Now, if T is equal to its adjoint, what's that implying about these entries in these matrices? Now we simply equate this matrix with that matrix, don't we? If they're equal, their matrix representations have to be equal, which says that A has to equal its complex conjugate. How's that going to happen? A has to be real, doesn't it? If A is a complex number and it equals its complex conjugate, we can't be changing the sign of the imaginary part and have that equal. So it can't have an imaginary component. A equal to A star says that that term is real if this matrix, if these maps are self-adjoint. What about E and E star? Real. I and I star. The diagonal entries are going to be real, aren't they? In a self-adjoint operator, in the matrix representation of a self-adjoint operator. So these are some relationships that we've just shown. A is equal to A star. E is equal to E star. I is equal to I star. Those are our diagonal elements. Those have to be real. And then what else do we know? Well, we know that B must be D star, and D is equal to B star. G is C star, and C is G star. And F is H star, and H is F star. And those are just our off-diagonal elements. The off-diagonal elements are conjugate pairs of each other. And we'll pick up at that point in Chapter 7 on Wednesday. But this now you can start thinking about the examples that we looked at and how this now moves us forward into Chapter 7.